Now we're going to move on to TJ McKinley, who is going to be presenting calibrating complex COVID models to partial data using Gaussian processes.
Brilliant, thank you, Kira. Can everyone see my slides and hear me all right? I assume so.
Yes, thanks, TJ.
Brilliant, thank you. So thanks very much for allowing me to come and talk. I'm going to break ranks slightly, and what I'm going to present here is ongoing work. So we were a little bit later to the party, I think, than a lot of the groups that have been presenting here. So we are really trying to develop techniques sort of to feed into the modelling efforts going forward, but also trying to put infrastructure in place to allow some of the uncertainty quantification techniques that I'm going to talk about today to allow them to be easier to implement for future pandemics. And this is joint work with lots and lots of people that you can see on the screen here. So this is, again, a sort of methodology talk. I'm not going to present any results, obviously, because we don't have any yet, but I'm going to hopefully give you a flavour of what we're trying to do. Now, Chris has given a very nice introduction into the challenges of doing statistical inference for these sorts of complex models. And I'm going to talk about the other side of that inference paradigm to what Chris talked about. So I'm going to talk specifically about particular versions of what we would call likelihood-free inference. So this work was originally motivated by Leon, who you've just heard talk. So Leon approached us, so it has a very nice paper with Thomas House and Matt Keeling in 2009 that was developing a discrete time stochastic metapopulation model. And so this is a simulation model, and the idea of that paper was to look at explicitly building in commuter information. So this is a metapopulation model which in that particular case was specified at the electoral ward level. Okay, so there's about 8,500 electoral wards in England. And the idea is that you have epidemics running in each ward, and then you have wards coupled together according to commuting data. So individuals can move between wards at different points of the day, and so on. And so right at the very beginning of the COVID pandemic, Leon, and in particular Christopher Woods at Bristol, took Leon's original code and have built a very flexible piece of software which we call MetaWards, and this really allows for some sort of quite complex dynamics and things to be built in. So it's effectively a flexible way of being able to write epidemic models, and it allows for all sorts of things like multiple pathways. It also allows for different demographics now, which we're going to try and use to build in age structure, for example, into the transmission process. And we can have different pathways for, say, asymptomatics or hospitalizations and so on and so forth. And so this, and of course, the advantage of this is that you can use MetaWards to specify the simulation at whatever spatial scale you have the data to support. So if anyone's interested, there's the website here, and Chris has written some really nice tutorials and things for how to specify different types of models. And obviously this is an ongoing piece of development. And so Leon approached us and kind of said, okay, well, you know, we've got this model and framework, and we might be able to use this to try and tackle some important questions. Can you help us try and calibrate it? So this is what we're going to try and do. So the idea, I'm not going to spend very much time on the model here, but this is the kind of current working version of what we're trying to do. So we have various different pathways. We have a sort of pathway through asymptomatics, we have a pathway through symptomatics, and then we have some individuals who go to hospitals, some that die in the community, some that die in hospital, recovered, and so on. And we also have a transmission structure here, which is going to have age dependence in this. So we're going to use the sort of contact matrix type data that Julia was talking about. And then we have transitions through these different pathways, and some of these parameters here will also have some age dependence. Now, all of the the idea of what we're trying to do is to put up all of the code and everything on a website. So there's a website here if anyone wants to have a look at it. The website at the moment contains mainly the preliminary work that we did at the beginning of the summer last year when we were sort of trying to settle this up before we got funding. But that will be updated in real time as we begin to get the models up together and the model runs. And so this version of the model is not on the website yet, but it will be fairly soon. So please don't read anything into the numbers here. This is just a random simulation that we pulled out. And this is just really to give you an idea of the sort of spatial structure. So this is a ward level simulation. And you can see that you can have quite fine spatial resolution. And so the key challenge here, so there's lots of kind of challenges of working with these models, but I'm going to focus mostly on the calibration problem. So in a sense, how do we learn, how do we fit the model to data in some kind of robust and efficient way? And the challenge here is that we have lots of parameters in this model, and we have some parameters that are age specific and some that are not age specific. And what we would like to do ultimately is to calibrate this model to things like hospital death data, which is specified at the NHS trust level. So we're not going to be fitting to ward level data, but we will be fitting to some aggregation of ward level data. And the challenge is, you know, if you've got this simulation model, this flexible framework for generating models, how do we, but we have a lot of parameters, how do we robustly explore the parameter space? So we want to understand the uncertainty that is inherent in the parameters, but we also then, once we have that, that allows us to propagate those uncertainties through when we're doing predictions or forecasting or whatever else. So this is a sort of full uncertainty quantification type framework for dealing with these kinds of models. So one of the, I mean, obviously the, you know, different inference approaches have advantages and disadvantages. And the simulation-based approaches have the advantage that in general, it's easier to specify models in a simulation framework than it is to specify models, say, using data augmentation. Okay? But obviously that is traded off against other considerations. And so it's kind of, Chris touched upon this earlier, but there are techniques that have arisen in the last sort of 10 or 15 years, so things like approximate Bayesian computation, which are specifically designed to work with these kind of black box models. So that it sort of, if you like, decouples the simulation model from the inference routine. The problem with this is that these techniques, even in very simple, very toy models, can often require hundreds of thousands or even millions of model runs, right? So the idea is that you explore the parameter space, you run the model at lots of points in that parameter space. The challenge there is that as you increase the number of parameters, what you're doing is increasing the volume of the parameter space that you have to search. And furthermore, if you want to match to or calibrate to larger amounts of data points, then you also require many more runs. So you can see that these things are going to compound in a model like MetaWards. And so in a sense, we're not able to use these kinds of techniques, right? Because one run of MetaWards, if you've got the full ward structure in there, I mean, even with the nice parallelization and things that Christopher has put into the code, we're talking about the order of minutes per simulation, right? And so we have this big complex model, large parameter space. We're simply not going to be able to run millions and millions of model runs. So really what we're trying to do is to now use techniques which have been specifically developed to try and calibrate these very expensive models. And these use what we call emulators. Okay, so if you imagine that so this is, I'll show you an example here, but if you imagine that we have our complicated model, okay, and the idea is that we can't evaluate that complicated model at large numbers of parameter points because it's too expensive. So what we're going to do instead is we're going to build a surrogate model, which we're going to call an emulator. Okay, and the idea is that the emulator is an approximation of our complex model, but it's a very fast approximation. So we can then, once we've trained the emulator, we can use the emulator to explore the parameter space and try and find areas where we think we're going to get good fits to the data. Okay. Now, just to give you a very simple example, so if you imagine here, so this is a one-dimensional example, okay, so I'm going to take a single parameter, okay, which varies along the x-axis here, and at some parameter value, I plug that into my model, my simulator, okay, my complex model, and I get a particular output, okay, which is here. So ideally, what I'd like to do is I'd like to run my simulator at large numbers of points across this space and find out what it predicts will happen. But I can't do that because my simulator is very expensive, so I can only run it at a few points, okay? So here I've run it at 6 points. So what I would want to do is I want to build an emulator which I can then evaluate at all the points in between these points, okay? And use the emulator to try and predict what the simulator would have given me at the points where I didn't run it. So what I need is a flexible way of defining this sort of model, and there are lots of ways of doing this, but one of the most common and most powerful is to use what we call Gaussian process regression. Okay, so the idea here is that I would use these inputs, the parameter inputs and the outputs here, to train a Gaussian process. And once I've trained that model and I've validated it, then I can use that I can run this at lots of inputs, and I can produce predictions for what my complex model would have given me. Okay, and so the mean prediction from my Gaussian process here is given by this blue line. Okay, so you can see that the blue line is essentially interpolating between these points. Also, the thing to bear in mind here is that the emulator is itself an approximation of my complex model, so there will be uncertainty, additional uncertainty that is associated with the use of an emulator. So these red bars here give you some prediction bounds on this prediction from the emulator. So this is potentially quite nice, and there are approaches which have been posited whereby you just simply train your emulator and then you plug your emulator in to whatever routine you're using, like ABC or whatever. The problem with that is that that ignores the fact that your emulator is itself approximate. And so if you want to ensure that you don't have or you want to ensure that your inference is accurate, then that requires that you have an emulator which is sufficiently accurate across the whole of the parameter space. And then, of course, the challenge is that in order to make an emulator accurate, you need a large number of training points. So therefore, you need to run the simulator a large number of times, and that's the thing that we can't do. So there is an alternative approach to doing this, which called history matching, which I'm going to go through shortly, which basically is a way of being able to efficiently search through the space that incorporates the uncertainty that's associated with the emulator, okay, and doesn't require that the emulator is perfect across the whole space. It just requires that the emulator is good enough to be able to search the space efficiently. Okay. So the way that history matching works, oh, sorry, I should say here, by the way, there's lots of other aspects of uncertainty quantification, so things like sensitivity analyses and things which have also been developed, which specifically use emulators. And so there's an aspect of this project that will also look at that, but I'm just going to focus here on the calibration problem. So the technique called history matching, what it does is it, rather than looking for bits of the space that are good, it kind of looks for bits of the space that are bad and then throws that out. Okay? And the way it does it is appeals to the use of what we call an implausibility measure. Okay, so if you imagine here that Y here corresponds to a data point that I want to calibrate to. And so this is an output. This is the thing that I'm trying to emulate. This expectation here corresponds to the emulator prediction at a given set of parameters theta. Okay, so that's this blue line that you can see in this plot here. And essentially what we would like to do is to find areas of the parameter space where we get good fits. Okay, so i.e. areas where the prediction is close to the data, or where this sort of numerator here is quite small. So what we do is we retain bits of the space where the implausibility is low. Okay, but the implausibility is not just a function of how far away the prediction is from the data point. It also gets divided by all of the different sources of uncertainty that are inherent in the model or the system. So we have things like observation error, we're emulating stochastic processes, so we have some error to do with the fact that the simulation model is itself uncertain. There's also additional error that we introduce, which is called model discrepancy. And this reflects the fact that the model, the simulator itself, is not real life. It's an approximation of real life. So we should have some additional uncertainty in our estimation process here. And then we have this, what I've called code uncertainty. So this is the emulator error, okay? Now, if you think about this, the areas where the implausibility are low are either because we are in a part of the parameter space where the emulator predicts a close match to the data, or alternatively, we are in a bit of the parameter space where we are very uncertain, okay? So the implausibility does not throw out bits of the space unless it is sure that you are unlikely to get good fits in that bit of the space. So just to illustrate this on this one-dimensional example, if you imagine now that this middle horizontal line is a data point, so what I'm doing is I'm trying to search this parameter space to find where my simulator will give me an output which is close to my data, okay? And these, the bars here correspond to some observation. Okay? So I've run my emulator and I calculate the implausibility, and what I'm going to do is apply a threshold, and I'm going to throw out any part of the space where the implausibility is bigger than this threshold. So if I do this here, you can see that I've immediately removed all of this red area here and this red area here, where even though the emulator has uncertainty associated with it, the predictions are far enough away from the data that I can remove it. And so what I get left with is this area in the middle here, and this is an area that we call the not ruled out yet space. And the idea here is that there could well be good fits within this region. So ideally what we then want to do is we want to run more simulator points, but this time, rather than having to run across the whole space, we can target them in this region here. So for example, I might then put another point in here and I run my simulator, and now of course I can refit the emulator, and the emulator has more information, so it has less uncertainty associated with it, and that then allows me to cut out more space, and then I might add another point in here and another point in here. And you can see that at this point now, the emulator is sufficiently accurate that adding more points in doesn't improve, doesn't reduce the uncertainty anymore, and so therefore I can stop. Okay, and you can see that this has now found two regions of the parameter space that are not ruled out yet. And obviously what we would then do is go in with our simulator and run some points in here and see whether we get good fits to the data within this region. So to summarize, history matching is a way of exploring the parameter space very efficiently using an emulator. And it's particularly well suited because we can, if we need to do millions and millions of evaluations, we can do that very quickly with an emulator, but we can't do it with the simulator. It's nice because it accounts for all the different areas of uncertainty, and it particularly accounts for the emulator uncertainty. Okay, and it means that the emulator doesn't have to be perfect. It just means it has to be good enough to get rid of space. And also it informs you where to put more design points. If you do something like ABC, the number of simulations that you run as you go through the ABC is itself a random variable. Here we can fix how many runs we want to do at each wave of this history matching process. And so that's really useful if you're trying to manage workloads and things on HPCs and so on. And we can extend this to emulate multiple outputs, and we can extend this to take, fit Gaussian processes where we have lots of parameters that are feeding into it. So and there's quite a lot of work that's been done on this. So these approaches have been used very effectively in lots of fields like climate modeling and astrophysics. They're only much more recently been employed in infectious disease modeling, okay, and mostly on HIV and Ebola. The challenge is that there is no general purpose software at the moment for doing both emulation and history matching. This is fairly recent methodological advances, and so we're trying to put together the infrastructure to do this. There's also lots of ways of building emulators, and there's no consensus, and what we have a group of people, and we're going to try and explore lots of different approaches, but if anyone else wants to take our data, then we'll also make all this available. Stochastic outputs, this is a stochastic simulation model, can induce challenging behavior, so things that are hard to emulate like non-stationarity, multimodality, and so on. And of course, if we were to do this for a novel outbreak, then we would also have to use prior elicitation techniques to try and constrain the parameter space in the early stages of the outbreak before you can do the calibration. And here we have large numbers of outputs. So, you know, if we're modeling at the NHS trust level, we're going to have a minimum of 250 emulators that we need to fit and validate, and so on. So there is still quite a lot of work that needs to be done in order to push this forward. And the final point is that if we want to use this for forecasting, then we would also ideally want to condition simulations in the future on the data that we have at the moment, which is called data assimilation. So more work needs to be done to do this. So MetaWards is a very powerful, flexible way of specifying models. But if we're going to be able to use these techniques to calibrate in real time, then we really need to put the infrastructure in place to do this. So all of our, as we progress through this, we're going to put all of our model runs on this open access website. So if anyone wants to download them and play around with their own emulators, then please do. And all of the model code will be made available at this website. So hopefully the whole process should be reproducible. And thanks very much to our funding. So we've got EPSRC funding and obviously JUNW funding as well. Thank you.
Great.
Sorry, I've overrun.
No, thanks, TJ. So I'll just do one quick question, which is actually from Chris Jewell. So how do you avoid missing a potential region of the parameter space where I theta is low? And also, how does the emulator perform when case numbers are low, i.e. when the Gaussian approximation gets worse?
So very good question. So there's an element, so we've done quite a lot of elicitation to try and cut down the regions of parameter space that we're going to explore initially. So yeah, generally the emulation gets harder with the larger the parameter space that you want to search. So a lot of these methods will use quite constrained parameter spaces, but we try to do that in a sensible kind of way. And your point about the low numbers of cases, so this is something which is an ongoing aspect of research, is to try and work out what particular challenges this sort of system throws up that many of the other systems that have been calibrated with these sorts of methods don't throw up. And definitely the low case numbers is an area where which we're looking into at the moment.
Great, thanks TJ. In the interest of time, I think we'll move on to Danny